So you have it. This is the most famous probability distribution that you can have. This is called the Gaussian distribution. So this is called the normalization of the wave function in quantum mechanics. Hi, so welcome back everyone. In the last couple of lectures, we had learned a few things. So let's briefly recap. One, we have learned that there is something called a wave function in quantum mechanics, typically denoted by a psi x of t, such that its integral over its norm between any arbitrary points xa and xp gives you the probability of the particle being between x equal to a, sorry, not xa, and x equal to b. This was broadly the content of lecture 1. We learned a bit more in lecture 2. We learned about probability measures, like the mean, the variance, which the mean we denoted by either the expectation value of x or equivalently x bar, the variance, which we called sigma square, and the standard deviation, which was essentially the square root of the variance. And we have shown that actually this guy is a positive definite quantity, so there's no problem in defining the standard deviation. And this was roughly the broad message of lecture 2. So the link for these 2 lectures would be in the description box if you guys are interested. So let's continue, and let's learn about one of the famous distributions called the normal distribution in this setting. So recall that what the definition of your mean was. Your mean was defined as, maybe I prefer the expectation value notation, as 1 by n summation over xi, where I runs from 1 to n for a discrete set of numbers. Actually, this is a set, so it can be anything. So this was defined as the mean, and we therefore naturally expected the higher moments. We had defined these moments before in lecture 2 as xi to the power small n I is equal to n. So these were all covered in lecture 2, by the way, if you guys are joining me for the first time. Then we talked about what a natural generalization would be. Natural generalization to the continuum domain, to the continuum? Well, these were discrete. Here, these were discrete. And that we know because this label was a countably finite discrete number. I was 1, 2, 3, whatever. So this was in the discrete space, and we already know actually how to make the sum go to the continuum domain. This we have learned in calculus, that summation signs get replaced by exactly integral signs, for example. So it's quite clear that for the continuous variables, you would get the following definitions. Minus infinity to infinity dx x times rho x. And this rho x is called the probability distribution. Function, actually, probability distribution function, PDF. Of course, the higher moments are equivalently defined. For example, oops. If you have an n here, you'd have an n here, right? It's easy peasy. Right. In fact, if you have any function here, we can do even better. So expectation value of any function would be simply this. This was math. In quantum mechanics, we borrowed exactly the same idea, and we defined an in essence, we have done nothing other than replace this. We have just chosen this row to be our wave function, such that this wave function satisfies this guy now, satisfies the Schrodinger equation. Okay, great. So all this fancy idea, let's work something out. For example, what do I want to do? For example, let's take a problem from Griffiths and solve it. So imagine someone gives you this row of x, which by that I mean this guy, to be equal to some unknown coefficient a e to the power minus lambda, e being exponential, x minus a small a whole square. And the goal is, or the exercise is, to, for example, go back and figure out these guys. All these fancy things that we have learned, we want to exactly explicitly work this out for a particular problem so that we have some understanding of what we are talking about. Okay, great. So 1, we know the particle, maybe I don't want to refer to the particle now. We know that the sum of probabilities has to be 1. Actually, I hope you understand what this line means, right? Let me explain. Say your mother, again, let's go back to the example that I gave in the first class. Say your mom asked you where you are, right? And you being rebellious, you don't want to tell her exactly where you are. You told her that you are in friend A's place with 1/3 probability, friend B's place with 1/3 probability, or friend C's place with 1/3 probabilities. But you are not lying, right? So you are definitely in friends, either at friends A's place or at friends B's place or at friends. I mean, either one of the three, right? So the probability of you being at friend A's place plus the probability of you being at friend B's place plus the probability of you being at friend C's place has to sum up to 1, right? You are in one of the three places. That's for sure, right? So that's basically the idea behind the probability summing up to 1, okay? Great. So now we know what it means when we say that probability sums up to 1, which as an equation, let's first write the discrete version, then we'll do the continuous version. So for the discrete version, this would be P of all the xi's equal to 1. This we again worked out in lecture 1. For the continuous version, now you know what this is going to be, right? This sum is going to be replaced by an integral of x going to minus infinity to plus infinity of this rho x, which means integral minus infinity to plus infinity rho x a exponential minus lambda x minus a whole square. Okay, this object needs to be equal to 1, right? This is the continuous version of this equation, right? Which means a times this integral, since a is actually a constant here, of course it's a constant, otherwise it wouldn't make sense. This is a constant here. It comes out of the integration and it becomes minus. Of course, maybe I could argue later, but this lambda needs to be positive actually. It could be complex though, but its magnitude needs to be positive. The reason for that is this needs to, for the integral to be well defined, this needs to go to 0, of course, as x mod x tends to infinity. Otherwise this integral would not converge, right? Okay. Is to be 1, and this we can easily perform this integral, and I have performed it for you. And what's the result? This integral actually evaluates to root pi by lambda. This you should check. which implies A is equal to lambda by pi. So already we have figured out one thing, which is this abstract constant that was sitting here, x independent, of course. Good. So now we know what the probability distribution. We know what the probability distribution is. This is lambda by pi. There is no a anymore. Exponential minus lambda x minus a whole square. Food for thought. You might want to think about this. Okay. In this a, the small a question, why is it independent of small a? The parameter sitting here. So let me know in the comments if you guys have figured it out. I'm not going to tell you immediately. So let me know, okay? That why is it that you have an equation that involves small a, but seemingly your capital A is actually independent of that small a. So let me know why you think that is. Okay. Okay, so now you have figured out the probability distribution function. While doing quantum mechanics, it's just that you would have figured out this ix again, just to tether our argument with respect to about quantum mechanics. You would figure this out, psi x, by solving a Schrodinger equation. That's all. That's all that's going to happen. In quantum mechanics, okay? Good. So we have figured out the PDF question. Then what are expectation value of x, expectation value of x square, and the standard deviation. We already know the formulas, right? If you guys have access to pen and paper, write it before I do. Okay, write out the formulas before I do. So expectation value of x is tick tock, tick tock, tick tock. You had 3 seconds. Did you write it? If you have, then check it with me. It should be dx x rho x integral over x running from minus infinity to plus infinity. Right? Which formula is this? Okay, let's check. Let's check if I've written it correctly. So this is this formula, right? This formula. The general formula. Just that fx is, in our case, just x. Good. And I have solved this on my own with rho a given in this equation, say equation 1. And this guy turns out to be equal to, should I give you a couple of seconds to do it? Okay, take your time. Tick tock, tick tock. This guy turns out to be simply A. Aha! Surprise, surprise. So finally the small a makes an appearance. I was wondering where it had gone, right? I mean, it was not there in the capital A. But, okay, good. So, did you do it with me? Did you do it on a pen and paper? Do you get small a? You should get small a. Okay, so what about the expectation value of x square. Again, same formula. Do it with me if you guys have access to a pen and paper, and if you're watching my video from a computer, do it with me. So it should be x square rho x, and this should be, I claim, you can check that this is actually 1 by 1 plus 2 square lambda pi 2 lambda. Check that this is correct. This is the next homework. So it's a lot of hard work, right? I have done all these on my own. So if you guys find these lectures helpful or interesting, and if you want to support me, then please click like and subscribe. Thank you. Okay, back to physics. So sigma we had defined. This was in a previous lecture, the links of which would be in the description box, and we had defined sigma to be this guy. We had actually also defined sigma, and they are equivalent expressions, to be this guy. The square root of it, of course. This is variance, and you need to take a square root. And you want to also do this as a homework, because now I have expressions for everything, right? I have this expression, which is this, and I have this expression, which is this. So it is 1 minus 1 plus 2 square lambda pi 2 lambda minus a square, because there is a square here, square root. This is, what is this? So this is 1 by 2 lambda. So you should check this out, that this actually is correct. You can do it with me. So upshot, your rho x was given by a exponential, what was it, minus lambda x minus a whole square, right? Minus lambda x minus a whole square. So from here I can substitute lambda to be equal to 1 by 2 sigma square, right? From this expression. Good. If I were, and of course a has been figured out in this step. So if I were to substitute it back, it would be, so this guy is, a is root lambda by pi exponential minus 1 by 2 sigma square x minus a whole square, with your lambda being 1 by sigma 1 by root 2 pi exponential minus 1 by 2 sigma square x minus a whole square, right? And this is Let me write it in a slightly, I beg your pardon, just hold on a second. Yeah, so this is this guy. So you have it. This is the most famous probability distribution that you can have. This is called the Gaussian distribution. Maybe some of you have already heard about it. Distribution. This is ubiquitous both in physics and in mathematics. And its probability distribution, the PDF, is given by this expression. So for the Gaussian distribution, you have sigma, its standard deviation, and this A as its mean. And if I were to plot it, last time we figured out what this sigma does. It would be symmetric. My drawing is not perfect. It would be symmetric about this axis. This would be the mean, x. This is x. This would be rho of x. And sigma controls this width, for example. This is the standard deviation. So there you have it. This is called the Gaussian distribution or the binomial distribution in physics and in maths. So I hope this was very, very clear. And yeah, so these please do these homeworks and let me know if you don't get them in your comments in the comment section. Okay. So borrowing this, I wanna just continue, and we will together we'll figure out let's figure out the normalization of the wave function, exactly analogous to what we did for the Gaussian distribution. It's just that instead of rho, you would have a sigma square. So note that from the Schrodinger equation, which we discussed in lecture 1, if I h delta psi xt is equal to minus h cross by 2 till capital psi x t till x square plus vx psi x. This was done on lecture 1, so if you guys are joining for the first time, please check out my first lecture. And the reason I wrote it is, note that if you were to multiply all of psi x comma t by some arbitrary constant, this equation 2 would still be satisfied, right? How do I see that? Well, it's easy to see. I multiply an a, say for example, I multiply an a here, and a here, and an a here. Like a constant a, of course, not a function of x or t, a constant, arbitrary constant. Then if I were to multiply this full equation, nothing changes, right? So this is an important point. The Schrodinger equation does not tell you the normalization, of course, because all of them are linear in psi, right? If it were, for example, when would this not work? For example, okay, let's give a counter example. For example, if this were psi square, right, then it wouldn't have worked, because if you were multiplying a psi by an a psi, then this would have gotten multiplied by an a, this would have gotten multiplied by an a, but this would have gotten multiplied by an a square because of the square here. So then it wouldn't have worked. Then it would have fixed the constant for you, but that is not the nature of Schrodinger equation. So Schrodinger equation doesn't fix this normalization constant for you. You need something else, some extra input from outside to fix this. And what is that extra input? We already know it. We know that, for example, since this gives you the probability of finding a particle somewhere, so this has to be 1, right? Because the particle is somewhere in the universe, right? So that's why I have integrated from minus infinity to plus infinity. So the particle is somewhere in the universe, and that is what this equation is telling you. That if I mean, this is exactly as saying that the sum of probabilities is 1. So this is exactly the continuous version of that equation. Right. So this equation will fix your wave function normalization, right? Imagine you have psi xt is, say, for some constant a times fxt, exactly as we did before for the binomial distribution, where we figured out this a, which a, this capital A. Where did we figure it out? Yeah, here. Exactly analogously, you do the same, and you would say, since of course now this is a mod square, you would say mod a square, because note that this can be a C number, right? This can be complex. Could be. Doesn't have to be, but could be. F xt square is equal to 1. This equation fixes the constant a uniquely. Is this clear? Because, imagine you multiply the both sides by alpha. That would change this one, right? 1 goes to alpha. It won't be invariant under that multiplication. So unlike, for example, this equation is invariant under arbitrary constant multiplication on the left hand side and the right hand side, but not here, right? Because here you have a fixed value. So yeah, so this is called the normalization of the wave function in quantum mechanics. This is exactly analogous to what we did for the binomial distribution. So it's simple, right? It's very simple. Okay. So that would be it for today. And so if you liked my course, my class, you know what to do, right? Kindly like, share, subscribe to show your support. And thank you. See you all in the next class. Bye. Have a good day.